Okay, welcome everybody. I still see people coming in, which is great. Right now you're on listen only mode, so you will be unable to talk to us at this point. However, we would love to get your questions in the chat box so that when there's a time for questions at the end, we can make sure we answer them. And my name is Jennifer Bourgeau. I am the United States Country Coordinator, so hopefully you read my email or you know of me from that role. I'm also the coordinator at the New Hampshire Globe Partnership. The seminar series or webinar series that we're going to be doing is in support of teachers that are submitting student research with the student team to the U.S. Globe Regional Science Fairs. And also it supports the Globe International Virtual Science Fair as well. This is a series of webinars, and it is funded because the National Science Foundation has funded a grant for us to offer the United States Regional Science Fairs, and there'll be 6 of them across the country. These are the webinars are starting today with conducting field investigations, and I'm hoping that this hooks you into what we're doing. And on November 19th, if you have any remaining questions, we're hoping that we answer them. We're going to do a short webinar about the regional science fairs in the United States and also about the project evaluation to share that with you. And then after that in December, we're really going to start breaking apart and hopefully providing you with a little bit of professional development on writing research questions, analyzing data, doing your claims and evidence, and writing conclusions and putting it all together. And we hope that this will support you in attending a regional science fair. Right now we have the dates for the Northeast and Mid-Atlantic one, which will be at NASA Goddard, and that'll be March 10th and 11th, which will be great because then you can also submit that project to the Globe International Virtual Science Fair on March 11th. And if you don't have the March 10th and 11th date, it's even better because you'll be able to submit to the March 11th Virtual Science Fair, get feedback, and hopefully submit an even better project to the one in the Midwest, if you're from the Midwest, or on May 20th and 21st, the Northwest. And also, I just heard that the Pacific one will probably be at the late March. And let's see, the Southeast, we're shooting for April. And the Southwest will actually also be May 20th and 21st. So I will update these dates. I just had the meeting and found those out, so I'll update those dates. And if you're wondering what region you're from, then here's the map. And we do have a page on the Globe website that will make sure that we get to you. And it will have all of the information and links to the future webinars and to the blog posts. So we're hoping for, and while we're on the blog posts, on the timeline, let me just bring that back up. You'll see it says teacher webinar and then it says blog. And what we're hoping is that after listening to this webinar, you go back and you try in your classroom some of the techniques or the resources or the activities that we share with you under this umbrella of this webinar. And what we're looking for are teachers to write a blog post about that particular webinar and how it went in the classroom. So it's teacher in practice. And we're hoping that it's not always successful and that you'll be able to share and reflect on what happened to give other teachers an idea of how it went in your classroom. There is funding, a small honorarium for writing that blog post. So if you go to the webinar and you're really excited about what you've seen and you go back and try it in the classroom, let me know, and I am happy to look at your blog post, and we'll be able to give you an honorarium and post it to the Globe website. Let's see. The other part that I want to tell you before I open the floor to Pat Otto, who's going to be talking to us about conducting field investigations, is that after this webinar, you're going to receive an email if you registered through the email link that will have links to the Google spreadsheet or the Google form where you can indicate how interested you are in doing the science fair. So we make sure that you are on our mailing list and you are getting the most up-to-date information. So please, if this is really intriguing to you, that link will be in there. Also, after this webinar in particular, there will be, and in that email, there will be a place where you can download a PDF saying that you attended the 1-hour webinar. So for those of you that may need professional development or proof that you were here and this is what you were doing, that is in that email as well. Let's see. I think that's it. There's also links directly to the Regional Globe Science Fair website in that email. So hopefully we see you more and more after each webinar. And with that, I'm going to turn it over to Pat Otto, who I met at the annual meeting of Project Learning Tree back in Saratoga Springs in New York. I met her in person. I'd always heard about her, and I was really excited to finally see her in person. We use her guide on field investigations in New Hampshire with our teachers. It's the foundation of our workshops with teachers and our work with teachers that we have Math Science Partnership funding for. And we work with teachers for 3 years from districts, and they're usually teams from K to 8. And we use this guide with every single group, and we revisit it every single year with each of our themes. So when the opportunity came to ask her to do this, I'm so happy she's here with us. So Pat, I'm going to turn it over to you. You have control.
Thank you, Jen. And thank you for such a kind introduction. Goodness gracious. So we are about field investigations today and the application with STEM. So it's bridging that natural curiosity of the learner with the pursuits of STEM. I'm going to be your guide today through the Field Investigation Guide from Pacific Education Institute. We're stationed here in Olympia, Washington, and this is our current guide cover. It is under revisions, and those revisions hopefully will be out by January. We've submitted them to be printed, so we're all done with the revisions, looking with the eye of next gen. And so that word field investigations using outdoor environments to foster student learning of scientific processes is now scientific practices, if any of you are familiar with next gen and science and engineering practices. And as Jen said, I am Pat Otto from the Pacific Education, and that's me in the green, looking at one of my favorite trees, which is vine maple. Our agenda for today is we're going to go over a little bit with the next generation science standards, 3-dimensional learning. Then we're going to go through the field investigation process, talking about background for students to develop their own questions, because that's really our idea, is for students to have enough idea of what makes a good question to come up with their own, because that's more empowering. So then we'll discuss types of field investigations. We'll be planning and carrying out an investigation, what that looks like, analyzing our data, and constructing argument and explanations. So as I mentioned, those next generation science standards, this is the symbol, and you'll be seeing that blue, orange, green theme throughout. So why field investigations? So in the next generation science and engineering practices, A focus on practices in the plural avoids the mistaken impression that there is one distinctive approach common to all science, a single scientific method. So we really want to expand because scientists in the real world do more than scientific method. Further, we want students need opportunities to design investigations so that they can learn the importance of such decisions as what to measure, what to keep constant, and how to select or construct data collection instruments that are appropriate to the needs of inquiry. They also need experiences that help them to recognize that the laboratory is not the sole domain for legitimate scientific inquiry, and that for many scientists, earth scientists, ethologists, ecologists, the laboratory is the natural world where experiments are conducted and data are collected in the field. Now, if you don't know what an ethologist is, you are not alone. I had to look this up when I first saw it in the framework. Those are animal behaviorists. And these are the 3 dimensions of the next generation science standards. So there's science and engineering practices, disciplinary core ideas, and cross-cutting concepts. And of course, as everybody loves to shorten things, you're going to now see SEPs, DCIs, and CCC. So remember those as we go through. The idea is that none of those are in isolation, and the idea of 3 dimensions is that at least 2 dimensionals will be happening at any one time in a lesson. You may not always be doing all 3, but at least you're going to be doing some disciplinary core idea, some cross-cutting concept, and some practices from engineering and science. So you're going to want that context application of those 3 dimensions. So let's look closer at those 3 dimensions. The first, of course, is science and engineering practices. Since I am a field investigation person, this is obviously my favorite, but no prejudice here. And this looks very similar to many of us what we did with inquiry, asking questions for science and defining problems for engineering, developing and using models when we investigate, planning and carrying out investigations, analyzing and interpreting data, using mathematics and computational thinking. That's sort of being explicit that mathematics is the language of one of the languages of science, constructing explanations for science and designing solutions, engaging in argument from evidence, and obtaining, evaluating, and communicating information. So even that last one we looked at what scientists do is that we really need to always be thinking about what research has happened before and continuing on. Then I'm skipping the disciplinary core ideas for a second and going to those cross-cutting concepts. And this to me is like the thinking skills of science, that in any, whether it's life, earth, or physical, or whatever investigation you're doing, you are always doing some of these thought processes and thinking about what's going on in your investigation. So you're looking for patterns, cause and effect, thinking about scale, proportion, and quantity, systems and system models, energy and matter, those flows, cycles, and conservation, structure and function of organisms, and stability and change. The disciplinary core ideas are the life, physical, and earth and space sciences, which we always think about as the core content of science, but now we've added a 4th one, which is engineering. Now if you notice, there are the science and engineering practices, and now engineering is showing up in disciplinary core ideas as well. This is very exciting. It really talks about that we want to apply what we learn. We want students to be able to apply what they learn in solving human problems and thinking about that problem solving, that critical thinking skills. So for our SEP, we're going to be engaging in field investigations. We're going to have to be setting the stage, and then we're going to be asking questions, planning and carrying out our investigation, analyzing, interpreting data, constructing explanations, and we're going to engage in argument from evidence. So systems understanding, what is a system? That background knowledge or systems understanding is critical for students to be able to come up with their own questions and to have good questions. So when I work with students, and these happen to be adult students in this photo, I ask them to draw and label a local system right outside their door. So we're not going to any place exotic. And then come up with questions about their system. What's going on in their system? This could be a local forest system. This could be an urban ecosystem. This could be a schoolyard system. So we're looking for those parts and thinking about having them ask questions. So here's a drawing. This group didn't label everything, but you'll see the sticky notes, and they've asked questions about their system on that sticky note to be thinking about what questions they can ask about that system. So that all is about asking questions. And today we're going to focus on two types of questions, just briefly on essential questions, and then we're going to be looking a closer look at investigation questions. Those essential questions are those big picture questions. They can't be answered with one investigation, and they connect various investigations. How healthy is my stream is an essential question. We often ask that with students, but you really have to do more than one investigation and more than one investigation in one place, because you can't talk about the health of the stream without doing more than one. The same if you want to think about how trees alter climate or their environment. Again, that's an essential question, taking in-depth observations and other investigations. Now in the current guide on page 11, it describes the three types of investigative questions we came up with. They're descriptive questions, comparative questions, and correlative questions. Descriptive questions are how many are given in a given area, how frequently does something happen, what is the temperature, speed, height, mass. So those are all those abiotic factors that you want to take measurements in a system. When does something happen? That flowering, fruiting, babies born, when mating occurs, when nesting occurs, all those important things. And when does something happen over time? An animal's range, all of those things, which can be quite complicated and demand a lot of thought in terms of those systems. Descriptive questions also happen in the laboratory. So when we think about the genome study, also when we go to Mars or we're looking at the bottom of the ocean, we're just finding out, and I shouldn't just say just, we are finding out what's there. And obviously it can be very complicated. So another example is when Lewis and Clark were out here in the Northwest, they were really asking what are the flora and fauna that live in this area. Now for comparative questions, we're really trying to see if there's a difference between a group, a condition, an organism, or populations of organisms. Is there a difference between or among different locations? And then thinking if there's a difference between different times, seasons, yearly, thinking about what happens from year to year, how changes occur. Think about that stability and change at the bottom of those cross-cutting concepts. So I just shortened those just so we can be thinking of organisms or populations, locations, I like to say locations or conditions, or times. So those are the three sort of broad categories for comparative questions. Again, a great example for comparative of between organisms, because that's sometimes hard to get a grip on, is thinking about Darwin's finches in the Galapagos Islands, where he was measuring beak sizes and then he was comparing them. Now correlative questions, what is the relationship between variable 1 and variable 2? What goes up when something goes down, and how does one variable change as another changes? Our biggest one to date is thinking of climate change and the CO2 levels measured at Mauna Loa, Hawaii, and the related various temperatures across the globe. Correlation data does not always have to be linear, as this typical predator-prey graph shows. It sometimes has an interconnection in a different way, so it doesn't have to always be linear. For me, thinking about what makes a correlative question as opposed to a comparative, because correlatives seem to be getting at cause and effect, which they do. But thinking about, and again, we have a little West Coast bias, and I know you probably are mostly from the East Coast and the Midwest, but that's okay. Douglas fir is big out here. How does elevation affect Douglas fir height? You would be measuring both elevation and tree height in this question. You would probably be doing a random sample and then taking both. And that would be correlative, because you would be measuring two different things. And a comparative, you would choose those elevations ahead of time, whether it's 1,000 feet, 2,000, 3,000 feet, and be comparing the heights of the trees. So that makes it a comparative. So that's like a very thin line, but that is sort of when you are measuring two variables and looking for a correlation between them, or if you've already decided something and you're comparing. I know in oceanic studies there's equipment that can do both. One, you have to go at specific levels, and the one takes data constantly. So thinking now in the guide now, there is a whole couple pages starting on page 12 for you to use to sort to get your teachers and kids. I know lots of teachers that use these with their students to understand the differences of questions, and it just really helps us talk about what makes a good question. So let's go through several of those now. Are water temperatures cooler in forested or non-forested streams? This is a comparative. We are looking at, you could say it's two locations or two conditions, whether the stream is forested or non-forested, and so you're making a comparison of those water temperatures. What types of birds use the school habitat during the year? That would be a descriptive, so you're finding out what birds come to that schoolyard habitat. And number 3, how do mouse populations change with hawk populations? This is correlative. You are measuring both mouse populations and hawk populations. You're doing censuses or a sampling of both of those. Now this fourth one, what is air temperature at the schoolyard throughout the year, sounds a lot like the bird one, the bird question throughout the year. But when I've worked with teachers and students on this, they want to say it's both. And it's sort of like the question isn't clear enough. It is descriptive that I'm going to be doing, going out and taking in a weather station my temperature every day. But then if I wanted to go back and measure and compare whether December or January are colder months, I could do that. So that again is where there's that always the borderline. Whenever we try to make categories, there's always those that need defining. So in the guide, it really wants to take students through the process, and they want to start with descriptive studies that we usually go out in schoolyards or forests and find out what's there, and then we want to move them to a comparative or correlative. And comparative is usually easiest because then we have specific things that we can measure. We're just measuring one thing, which is easier for students sometimes. So in this, I recently did this investigation with students, what types of trees grow in this forest at Rainbow Lodge. That's in North Bend, Washington. And then you could really turn that into which type of tree is most abundant in the forest at Rainbow Lodge, North Bend, Washington. So you're comparing the percentage of trees, of different types of trees. Now some people say, oh, that really looks descriptive, but if you were looking at conifers versus evergreens, then it feels more comparative. So yes, you can be looking at the different percentages of different types of trees to make that comparison and then be able to write conclusions. So they just spent quite a bit of time asking questions, that first bullet from Science and Engineering Practices. And I should mention that these are 1 through 8, but in reality, they should have dots before them because the process goes back and forth just like it does in real science, but it makes it easier to talk about those. And then again, what we've just done with our question sorting lesson is looking at patterns, thinking about cause and effect, and systems and systems models, that we're thinking about that system at the beginning, and now we're asking questions about that system to understand that system better. So let's proceed as if we were having students go out and explore some more what plants, animals, and fungi use the schoolyard habitat. So we'd start with this descriptive question, and then we'd start asking comparative questions. Here's just an example from 5th grade students in Arlington Elementary in Tacoma. You can see their animal observations and what they saw, and on the right hand of the screen are the questions they started to ask. And so some of those are comparative, but some of them are also further descriptions that they can do. Now these students had 4 opportunities to make observations before they did their questions, so that really enriches how much students can come up with questions, more background they have. For an abiotic measurement, since temperature is something that we are all familiar with our daily lives, now we've used that example in the book for our temperature for our comparative investigation. Now, not only do we need the background knowledge of knowing where they were going to take temperatures, but students need to connect with their background knowledge about temperature. So first thinking about, is the temperature outside in the schoolyard the same in every place? Thinking about how about a hot sunny day and you are wearing a black t-shirt, how does it feel? And we want to give students opportunities to turn and talk about that so that they connect with that background knowledge of what they know about temperature and sunlight. Our essential question for this investigation is, how does temperatures vary in different microclimates? And then our comparative investigation question becomes, which surface on the open grass, under a bush, or on the blacktop has the highest temperature in degrees Celsius in the schoolyard? So again, we want students to be able to come up with their own questions. So a good comparative question will tell us what we're going to manipulate, what we're going to compare, what is that independent variable. So I have students underline the independent manipulated variable, and that's the surface, the 3 different surfaces. That's what we're changing for a comparison. Again, a good question will also tell us what we're going to measure. So I have students double underline what we're going to measure, that responding dependent variable, in their question. So those things need to be in a question. For their investigation, they also need to keep things the same, whether they're control variables or, as the initial NGSS paragraph talked about, what needs to be kept constant. And I'm sure you will come up with others. So the type of thermometer, the wait time until taking temperature, shading thermometer so sun doesn't hit it directly, calibrating the thermometer or wait time outside, and the angle of the thermometer of the surface, and other ideas I'm sure that you have come up with. And on page 29 of the guide is a data chart that tells the students how they're going to record their data. And one of the items is date, time, and place, and you will hear this broken record from me because field investigations are unique in investigations. You need to know that date, time, and place, because temperature is a great example for this, because your temperatures in the morning, in the afternoon, on different dates and different places are going to be very different. I live near the water, so I get to be a little cooler in the summer and a little warmer in the winter. List of materials, thermometer, stopwatch, and for this one we added the 3 surfaces that we have available. Predictions. Now, next generation for hypothesis and predictions, they have had a de-emphasis on them in terms of you didn't see it as part of the science and engineering practices, but we still want students to be able to predict and think about reasons, and that will help them later with their claims, evidence, and reasoning, because we know people, when they predict, that then they remember things better. So we do want them to predict which condition will have the highest temperature. So we would have them write a prediction of which surface, and the data we're going to look at today is from a sunny afternoon in March here in the Northwest. Yes, we have sunshine occasionally. And which surface do you think will have the highest temperature? So then we're going to go outside, and we're going to collect our data, carry out that investigation. And here's the data we collected on that sunny afternoon back in 2005, a long time ago. And we're going to calculate the average temperature for class trials. And this is on page 31 of the current guide. Then when we're looking at that data, we may want to make line graphs, bar graphs, or place the data on maps to get an idea, a better idea of using that mathematics to understand or look for patterns. For younger students, we're going to be doing medians and modes. And then we're probably only going to compare 2 surfaces because that's easier for the younger students. And here, using a number line with younger students, and this is on page 31, you can clearly see that the blacktop surface has the highest temperature in this data taken on that day in March. So now what we've just gone over is planning and carrying out the investigation. we've analyzed and interpreted our data using that mathematics of making graphs and charts and using maps and thinking about that computational thinking to get that information out. And by doing that, now we can look for patterns in the data. We can think of cause and effect relationships. And because this is a temperature study, we're also thinking about that energy of matter, that what's flowing and what's changing, that sunlight and those different surfaces, the heat energy, the thermal energy that's happening in the system. And if we think about those disciplinary core ideas, those bigger ideas, we are conducting with life science and earth science and space science and thinking about changes in our environment. So now what's new, what's really the shift from conclusions with the next generation science standards is constructing explanations and engaging in argument from evidence. So that's what we're going to focus a little bit now. And what we use for argument and explanation is called claim, evidence, and reasoning. And I'm sure most of you have heard about using this template. So in a broad sense, the claim limits the claim to place, date, and time of a study. Now this is unique to field studies, and for any assessment of next generation claim argument, claim, evidence, and reasoning, you probably not see that, but again, I'm a broken record about for field studies, so limit your claim to your date, time, and place. And you want the claim to directly respond to the question. So our question, which surface on the open grass, under the bush, or in the blacktop has the highest surface temperature? So in the temperature study, this clearly would describe which surface has the highest temperature or describes that there are no differences among surface temperatures. And again, we want to limit the claim to date, time, and place. An example would be, with the data we had, is at Dearborn Park Elementary on March 18, 2005 at 2:30 p.m., the blacktop had the highest average surface temperature. So it answers the question and it limits it to the date, time, and place. Now for the evidence to support that claim, we need that evidence to be appropriate. Those are measurements and or observations that are relevant to the claim. And then we want to use averages or totals or estimations of what was measured or observed. We don't want those trial data. We want what was the final. We want sufficient. We want enough data to share the trends of the data without giving all the data. And enough data is given to share the range of data from different conditions, organisms, locations, or times. So in the temperature investigation, we would need to give the average, the mean, median, or mode temperature data. And for it to be sufficient, we would need to give average temperature data for all three surfaces. But we wouldn't want to give all the data when we're sharing what's going on in this investigation. So an example, the average blacktop surface temperature was 17 degrees Celsius. So we want to give real data from the data table. On the grass had the lowest average surface temperature of 10 degrees Celsius, while under the bushes was an average of 11 degrees Celsius. And now we would have students turn and talk. We might actually have them turn and talk, or at least discuss after they've collected their data about what it means. But at least now when they've made a claim, they've thought about their claim and the evidence that supports it, you want to give them chances to discuss that. I was recently at a conference. It was very fun. We put in just sticks in every time we'd say, this is my claim and my evidence, and the next person had to say whether or not they agreed and what their evidence was. And it really was a chance to talk and think about and learn more in terms of what you wanted to say. So reasoning part, and this is the really new part because the claim and the evidence looks a lot like a conclusion. And the reasoning may be something many of you as scientists you already did. But as students, we weren't asking them to do this as much. It just needs to stand out. Don't repeat the claim or evidence. It links. So you want to link what your evidence is with your claim. You want to describe, is there enough evidence to support the claim? And you want to describe the method of investigation that validates your data. And you want to include a scientific concept. You want to give it that connects your evidence with your claim. And you want that concept to be clear and to be accurate. For our temperature study, this means that the link would be telling us why there's enough evidence to support the claim. And for the science concept, here's some possible examples. They might include darker colors absorb more sunlight, making them warmer than other colored objects. That's in an elementary explanation. Bushes and vegetation can shade the surface from direct sunlight, and therefore the surface will be cooler. If you are more advanced, students might know about transpiration and the cooling effects of that. Without direct sunlight, cloudy day, to be absorbed, all surface locations will be similar to the ground or the air because heat will be transferred to the surface from the ground to the air. So this is what it would look like in our investigation with our data. The blacktop was 77 degrees Celsius warmer than the open grass, so this was enough of a difference, even with our small sample size, to indicate that the blacktop was the hottest surface. The blacktop had the highest temperature of any of the three surfaces in the sunny day because dark colors, just like my black t-shirt, absorb more sunlight and get warmer than other colors. Both on the grass and under the bushes had green plants covering the surface so they didn't absorb as much light and doesn't get as warm. And again, we would have students turn and talk about their reasoning so that they would have a chance to discuss other people's ideas and be able to clarify their own ideas in what they were talking about. So what happens now if your data wasn't different? And here we have an example from Tumwater, Washington on a cloud cold morning on December 7th, where all the averages of the surfaces were 7 degrees Celsius. Our claim would be that at the Tumwater District Office on December 7, 2005, all the surfaces, blacktop, open grass, and under the bushes had the same temperature, so no surface had the highest temperature. Our evidence would be all three surfaces had the same average temperature of 7 degrees Celsius. And our reasoning, so again, we would turn and talk. I don't want to leave that out because that's an important aspect of what NextGen is talking about. There were 4 trials at each location, so I think that this was enough evidence to make a claim about the surface temperatures at these locations. The weather was cloudy and cold, and surface temperatures were measured in the morning. The surfaces received no direct sunlight during the morning and probably for days. That's a side comment. Thus, all the surfaces were the same since there was no direct sunlight to be absorbed by the darker surface to make them warmer. Just like on a cloudy day, a dark t-shirt doesn't make you warmer. And again, we would be turning and talking. So now we've just done a brief constructing explanations and engaging an argument, and I know you're going to have a whole webinar on that, so I'm probably going to check in on that because I think this constructing explanations and engaging an argument is something we're all exploring and learning more about with next generation science standards. So again, our cross-cutting concepts, now we've expanded. We're still doing all those things, looking for patterns, cause and effect, particularly now as we're analyzing and trying to make those claims and evidence and arguments about our claims. Systems and system models, and energy and matter flow. So now we're going to look closer at this disciplinary core ideas. And here we have from the standards of 3 in terms of at 4th grade, there's a biogeology standard that living things can affect the physical characteristics of their regions. So here we have students looking at temperature and seeing how vegetation has affected the temperature versus the man-made surface. And at middle school in earth sciences, we're thinking of how human activities have altered the biosphere and also looking at the connections between the range of global the changes have happened in the biosphere. And gather evidence on how the planet's geosphere, atmosphere, and biosphere are interconnected. So we're thinking of surface temperature and the urban ecosystem. By having students then elaborate, or they can really delve into that disciplinary core idea. So we've done it about temperature, and now we want them, they have done an investigation, now we want them to understand it further. We could have students read nonfiction articles about microclimates, light absorption, heat islands, and this would add them allow more to their reasoning statements. There's a whole big list here, and I won't go through all of them, but they could also be doing, elementary students could be putting thermometers in black envelopes and white envelopes and then understanding under light which gets warmer. So again, that gives them more evidence for understanding what's going on in their system. Having students discuss more what inputs into the system would change, how can that change? Think about actions or decisions we might meant to make. So I've made a short list for these about having students discuss energy transfer and transformation, of understanding that light is transformed into heat energy when it hits air molecules or objects, and how different colors absorb different amounts, and that transfer occurs differently. Heat islands, microclimates, thinking about those further investigations. And lastly, and most importantly, what this information means in terms of their local system, and thinking about what is going on in that system. So that's a quick travel through the field investigation guide, and here's just a slide of the other guides the Pacific Education Resources offers, and from field investigation to project-based learning to sustainable tomorrow. So thank you all for joining me today, and we're opening it up to questions. Correct, Jen?
That is correct. And all of your guides are available for free, right?
Right. They're all downloadable for free. Correct.
Okay. So I included the link in the email to the page with all of your guides.
Wonderful.
So if there's anything there that looks intriguing to everybody or to anybody, then the link is there in the follow-up email for all of you. So I am thinking that I can unmute people, or you could raise your hand. So I'm thinking we'll take the risk and we'll unmute you all. And if people have questions, we just ask that you then raise your hand or use the chat window in order to ask it. And we have about 17 minutes for questions because we will be stopping on time.
The conference is no longer in listen-only mode.
So everybody might want to mute unless you're asking a question, and I'll leave that to you to do. Or you can also send me a message in the chat if you are unable to mute yourself, and we'll see if we can do that too. So does anybody have any questions for Pat? There you go, Pat. You did such a great job. Nobody has any questions.
I thought of one, Pat. This is Jessica Slodwick. I'm in Connecticut. Hello.
Hi there, Jessica.
Hi. I was wondering at what stage you would encourage the students to do their background research as they start working on references and a bibliography. I don't know if I caught when you said at what stage they should be doing their background research.
Well, for me, some of the background is understanding the landscape where they're going to be doing their investigations. So I actually like to have them explore and do some just investigating out wherever their field is, whether it's outside their classroom or a forest or a lake. And then I like them doing the research later so that they have that hands-on experience first. And then maybe go back and do further. Did that come through? I'm getting music.
Yes, I heard you.
I'm getting music as well.
So Jessica, yeah, you heard that. So I like them to explore and do some investigations initially, and then to do more research, sort of that evaluating other people, what's going on, or finding out what plants and animals are there.
Okay, thank you.
I'm trying to use the 10-second rule.
This is Dave Podlowski. I was just going to compliment the nice job that was done. It's very clear, and I enjoyed your perspective on it and look forward to downloading those resources.
Okay, thank you very much.
Pat, can you just go back over the emphasis you put on the time, location, date for field investigations and why that's so important? I think GLOBE fits very nicely with that because in each of our study sites we record the time, the date, and the location with GPS.
Right.
But can you just again expand on that particular one and what makes field investigations so different from maybe some of the other science investigations that people do in their classrooms?
Right. So part of it is in the field there's always those, we call them confounding, things that can be influencing your investigation. And by knowing that date, time, and place, then other people can come back and do their investigation the same way and then make a comparison. But if you didn't know that date, time, and place, you have no reference and sort of no context on. Certainly temperature has become, having done it for years now, is a fascinating phenomena in terms of how like a asphalt surface in the evening will really radiate its heat back out quite quickly. So in the evening you probably have those temperatures would be much lower. Where under a bush has probably got the most constant temperature. And so there's this fascinating, but you really need to know that date, time, and place to make any comparisons or any sense of that data. So like you said with GLOBE protocols, that's key to understanding. And certainly here we do a great descriptive study in terms of nature mapping and asking people just to tell what's here, because we don't know. How do we know if things are changing, that change in stability, if we don't have a baseline? And you need to know when and what season that happens so we can understand those changes, and even as climate change in terms of when flowering is happening and when bud burst is happening. Those are key to understanding the changes in our world.
Hello?
Hello.
Hi. This is Steve France over here in Akron, Ohio. And we are in a state where we do not follow next generation science standards. And I know every year my students have a lot of issues with trying to formulate their conclusion.
Right.
So and I have students in the room with me right now, and yeah, they're all saying hi.
Hi. How cool is this?
So anyway, as I'm looking at it, and we're having little sidebars here as well, I think really breaking down the claim, evidence, and reasoning makes that conclusion piece much more clear. Again, because next generation science standards, we really don't follow that here in Ohio. So I think especially my students really appreciate, and I do too, breaking that down into these components to hopefully make their conclusions much more solid
Right.
this year. So thank you very much for that.
You're welcome.
Not really a question, but a comment.
Thank you. I enjoy those comments. Thank you. And for me as a field investigator, I think the claim, evidence, reasoning, going from at least in our state, how we looked at conclusions, is empowering, because now, like that first, what plants, animals, and fungi use my habitat, you can now turn that question into an actual yes-no question. Do you think the schoolyard is habitat for a diversity of organisms? And so now with claims evidence reasoning, you can really do a yes answer or no answer, but now you have to claim it and provide evidence and then give reasoning. And so that sort of expands where in the conclusion people were sort of like, oh, yes, no, then I just would say, yes, it is, or no, it isn't. But now we know we have to give evidence, and I think that's exciting.
I think that piece in the turn and talk and giving those different claims and evidence and reasoning, well, one of the challenges to me for doing field investigations is that uncomfortable feeling of, I don't know if I have the right answer.
Right.
But by doing the claims and evidence and reasoning and turn and talk and having to defend your claim gives you more confidence, I think, in being able to say, I didn't know the answer, but this is what my data is showing.
Good point.
And so there's that, hopefully, it gets you over that hump of being incredibly uncomfortable of, well, field investigations is, who knows, because there are all these things influencing what's happening out here.
Yeah.
But then you can go back to that data.
Yeah. And Jen, I like that too, that there isn't a right answer when you go out there. It does change between, the morning and the afternoon, and so kids really have to rely on what their tools are measuring. They really have to rely on themselves, and I really like that aspect as well.
Other questions from the group online? Pat, I'll just ask briefly then, were there other we use fostering outdoor observation skills in that guide as well. Were there other guides that you could recommend for GLOBE teachers that might be more relevant?
Certainly the schoolyard biodiversity, it really is sort of looks at that in the field investigation model, so it's like a subset of field investigations. And then the project-based learning model, it's sort of more the engineering process. So that's one to look at in terms of solving problems. So you start with a problem, you try to evaluate. So that really looks very similar to engineering design. So that would be another, if people are interested, or once you've done a field investigation, they're thinking about whether it's a heat island or an area that's warm, or their school's warm and they want to plant trees or something, of doing some problem solving with the information they have.
I'm not used to a really quiet group. Especially Dave, you usually have 1,000 questions. Must have been our meeting before this.
Must have been.
Any other questions for Pat? Okay, then what I'll do is I'll remind you of the next one of these, which will be on November 19th. It'll be a question and answer about the regional science fairs, and also a description of the project evaluation and what that will involve. And then December 2nd is when we really start into taking each of the pieces that Pat gave us an overview of and breaking that down, we're going to have a lot of connections to GLOBE resources that are already there, and hopefully we'll be gathering them together under an umbrella of these webinars so that all those resources, you'll have those at your fingertips under each of these topics. Each of these topics have also already had a webinar offered at one point around some of them, and so we'll be linking you to those as well. So hopefully we'll be adding to our library about each of these topics. And so December 2nd, and then in January we'll be doing analyzing data and supporting claims with evidence and writing conclusions. The February 11th one, again, we'll be putting it all together in the communications, so hopefully those will give you some resources that you can use for students putting together those final submissions for the virtual science fair and also for the in-person face-to-face regional science fair. So that's what's coming up. And then again, this is when your regional science fairs are and where they are. So hopefully, Pat, May 20th and 21st, we're at the World Forestry Center in Portland, Oregon, so maybe you can stop by.
I would love to be there, yeah.
that
would be cool.
Great. And in case you didn't know your particular state and where you belong, this is on the website as well, but then you can figure out where you're going to. So you're going to Houston, Texas, if you're in the Southwest. You're going to Mississippi, if you're in the Southeast. NASA Goddard is the Northeast. The Midwest is at the University of Toledo. And the World Forestry Center is the Northwest. So we have some really great sites for everybody to go to, and we do hope to see you at the next webinars and definitely at the regional science fairs. Any other questions or last thoughts? So hopefully you'll find out about these and pass on the word about the webinars, and check the website, and also be watching the GLOBE emails where all the information will be. And all of you did a fantastic job muting, and I didn't have to pull that mute all button. So thank you. And maybe you'll be more talkative next time.
Thanks, Pat and Jennifer. That was really great for professional development. I look forward to more webinars.
Well,
Thank
thank
you.
you for coming.
Pat. Thank you.
Thank you.
Thanks, everybody.
2, 3. We can make some noise.
All right. Thank you.
Bye-bye.
Bye-bye. Thank you so much for having me.
Thank you, Pat.